you share your screen. And once you get started, we'll just, you can go ahead and. All right, everyone. Hi, everyone. So this is the XC demo session, software testing 3. We will have 3 demo related to software testing in this session today. We will wait for 1 minute for other attenders to come, and then we will begin our session. So let's wait for 1 more minute. Started, our first speaker is Alexander Prochnow.
Yeah.
Am I pronouncing correctly?
Yep.
He's from Germany, and he'll be presenting DiffWatch. Watch out for the evolving differential testing in deep learning libraries. So, Alexander, I'll give it to you.
All right, thank you. So I would like to present DiffWatch today. It's a tool we've developed for cataloging and managing differential unit tests in deep learning libraries. I will first talk about some background and motivation for why we developed this tool. Then I will give an overview of the tool itself and finally demonstrate some use cases and also talk about results. So let's start with why we developed this tool. An increasing number of deep learning applications today are built to perform critical tasks, such as recognizing cancer from MRI scans or autonomous driving. This has created a need for new methods specifically designed to test these deep learning applications, ensuring that they function safely and reliably. Since many of these applications are built using an open source deep learning library, such as TensorFlow or PyTorch, the testing of these libraries has become a focus of recent research. So when we were reviewing research in this field, we saw potential in the particular testing technique of differential testing and began analyzing current and past differential testing practices in deep learning libraries. So for a background, differential testing describes a category of unit tests that compare the output of the code under test with the output of an equivalent function from an external library. This is particularly useful for deep learning libraries because it allows the comparison of neural network model outputs, which were generated from different deep learning libraries. Differential testing might thus detect inconsistencies between deep learning libraries, which those may then be an indication of bugs existing in either library. So although differential testing helps ease the oracle problem that we face in general in testing, it also poses new maintenance challenges. Because of external code evolution, developers or maintainers of deep learning libraries need to be constantly aware of new changes to the involved external libraries, and how such changes may impact the use of differential testing in their deep learning library. So for this, we created a tool designed to aid the developers of deep learning libraries to manage their differential testing by automatically cataloging differential test cases. Since these test cases may need to be updated whenever the code of an external library evolves, the tool additionally allows developers to monitor changes in external libraries. This may help the developers to adequately react to the mentioned code evolution of external libraries. So the tool that we implemented it as a Python package. And for the next part of the presentation, I will demonstrate some use cases for each part of the tool. So let's first look at the automatic cataloging of differential test cases. For this, we created two functions in the Python package of our tool. The first one being the debug single file extraction, which shows us the test cases found in a single source file and the external functions extracted from them. So we can see an output of that function here. This works with any Python source file because we parse it into an abstract syntax tree, which our extraction algorithm then traverses. We can also have this function show a detailed log of the steps that the extraction algorithm took to identify a differential test case and the external function used in it, which is useful for debugging. The second function is the function to create a full catalog of test cases, which I mentioned earlier. That's the extract diff test cases function. This takes a while to execute, and at the end, we get the data stored in the form of a CSV file. The most important field here being the last one, the extracted external function. So now that we have the catalog of which test cases use which external functions, we would now want to monitor the repositories where the external functions came from. So a possible practice for the maintenance of differential testing in general could now be the following. Whenever there's a new release of an external package in use, we first select all of the test cases that use this package. In this example, we use SciPy, and we wrote a function that does this for developers. They just have to enter the name of the package or library that they're interested in. With the cases selected, we can then produce a HTML output document containing the changes made to the external functions. Here, the user just has to select the release date of the package version they're currently using in their library, as well as the version that they would like to upgrade to. The output document then contains git diffs for each external function. We do this by using the Git repository link to create a bare clone of the commit data and file changes, and then present relevant ones in a formatted way to the user. So let's have a look at one of these output documents. This is pretty much what it looks like. At the top, we have just general information about the two commits that we selected. And then we have the extracted data grouped by the external source file that that our extraction algorithm identifies. And then at the bottom, a collapsible git diff where we can see the changes highlighted so that developers then might take an action and say, we need to change our tests here or not. This example here is from TensorFlow checking against Keras, where they compare the RNN. All right. Finally, we then built analysis functions that show statistics about the coverage we achieved with the extraction algorithm. We also built an automation that lets us quickly inspect the data extracted by our algorithm alongside the relevant part of the source code from the deep learning library. These functions can be useful for developers to find areas where they can fine-tune our extraction algorithm to their specific library. More about the usage of these functions can be found in our GitHub repository alongside the Python package for you to try out yourself. So thanks for listening, and I'm looking forward to your questions.
All right. Thanks, Alexander. Any questions from the audience? Because I have a couple of questions, but I want to see if our audience have questions. From other presenter? No, other presenters are pretty nervous about their own presentation. Okay, so I have actually two questions. So first question is that how do people know that the two functions in two different libraries, right? At the beginning, you say there will be a mapping from one function to another. So how do people know that at the beginning these two functions in different libraries supposed to perform the same functionality? Are they referring to some kind of API document? They do that through experience, or how they construct that mapping at first place?
Well, I mean, in the first place, it would be our hope that developers use differential testing in general more, because it's a really nice way of testing, especially for cases like deep learning where the oracle is hard to come by. But once the developers actually wrote the functions once, our automatic extraction algorithm will identify the external functions that they use and automatically then sort of make that connection with the external library and give them feedback for an update if they should update their test case or not. Did that answer questions?
Yeah, but the reason why I ask is that because different libraries were written by different developers, right? Their design, their modularization could be different, right? So it could be like in one library, a function perform one functionality, but in another library, a function may perform the functionality combining two functions in another library, right? Because the whole design could be different. Then in this case, probably it might be challenging to find the mapping function of the one library to another. That's the reason why I asked. But of course, if in reality their design will be pretty much the same, then yes, I think we can construct that mapping, right? But I'm not sure whether they have the same design or same level of granularity or not.
Yeah, that's a really good point. I mean, that's maybe one of the reasons why differential testing is not so widespread at the moment, because it is hard to find other libraries that implement functions in the same way. So one good example of where it does work is with probability distributions, because there you can do things like test the expected value. And usually if you compare something like TensorFlow versus SciPy, the probability distributions will be the same. So there you have a good mapping and you can do differential testing. And in some cases with deep learning libraries as well, where the model is simple enough. But as soon as you get into more complex things, different libraries will definitely diverge and you'll have a problem constructing them, right?
Mm-hmm. And I do have another question. So I see that you are actually kind of tracking changes on the test to track the changes of the external library, right? If I understand it correctly. So the thing is, if one external function evolved to be different than your function, right? Then how developers usually react. Because if they are different, then maybe you cannot use differential testing anymore, right? Or you need to pick another function from another library. So how people will react when that change happens.
It's a good issue. I mean, that's what our problem tries to help what our tool tries to help the developers with, is at least make this decision or be aware of something like you were mentioning where it would break your tests. So in this case, developers would probably say, okay, damn, we can't do differential testing with that external library anymore, or with that function anymore. And then they would have to find alternatives or do some other form of testing. But at least with our tool, the developer then knows about and can look at the changes and see if they can continue doing differential testing or not.
Okay. Okay, I think we are right on 15 minutes. So any other question? Because we do have a 5 minutes buffer time. If no, we can move on to the second presentation, which is by Xiaoying. The paper's title is VR Test, an extensible framework for automatic testing of virtual reality scenes.
Thanks, Wei, for the introduction. Yeah. I do the sharing. Okay, so good morning, everyone. So I'm going to present my work on like a VR test, extensible framework for automatic testing of virtual reality things. So this is the work of this poor guy who does not have any student to work for him currently. So first of all, some background. So the virtual reality is our emerging technique allowing various applications like training, education, data, and system visualization, and also entertainment. And the difference between UI testing or traditional UI testing, right? VR is still considered as a type of UI, but the traditional UI testing and the VR testing has very different. The major three reasons are, first of all, the VR testing, which because it's a 3D space, it has a much larger search space. So you can move your camera from anywhere to anywhere in many cases, and you have one more dimension to go. And the object may occlude each other. So in a traditional 2D graphic user interface, if something is occluding another thing, for example, a button is occluding another button, then that is a bug, right? It's not really a problem. It's not really a. It's an issue with the software, but it's typically not going to happen in testing. So in testing, you're not really going to worry about if the buttons are occluding each other. It's maybe a part of the oracle. But in the VR applications, the object may occlude each other, but you need to bypass that object to go to another, to be able to see another object. And the object also may move from one place to another. So this gives the motivation to our VR test, which is automatic testing framework for Unity VR applications. We do this for Unity because Unity is widely used. It's over 60% market share for VR development. Our VR test features including tracking all the interactable and non-interactable objects in the VR scene. Remember, we need to know all the location of all the objects to find out a way to reach the interactable objects. And we also implement some basic camera features such as rotating, moving, point clicking, so that you can control the basic camera. And finally, we provide the callbacks for any new test strategies. So if you develop a new test strategies, you can use our callback interface to enhance the framework, or basically incorporate into the framework. So let's see the overview of this framework. So we have let me use this laser pointer. Yeah. So you have like a VRC, that is something you want to test. And we have a VRC monitor that reads the current state of the scene. Basically, where are all the objects, how large they are, and where they are they interactable, whether they have been triggered or not, right? And this information is being sent into the exploration controller. And then the exploration controller is going to make a decision based on the task configure interface, which is something that you do before the testing, and also the move, turn, trigger. These are 3 callback functions, and you need to implement a certain technique to guide the controller of the camera to do a move, a turn, or a trigger when you got the state information from the scene monitor. And after that, when you got the when you have the things triggered, and you're going to have the virtual object instrumenter to instrument newly created objects. So the reason for having a virtual object instrumenter at runtime is because like in VRSync, it's very common that you're creating a new object at runtime, or like removing an object at runtime, right? So we need to update like the instrumenters of all the objects, and then this is being sent to the VR thing, and then we are getting the VRC information again, and then this like whole thing is running during the testing. And then we're going to introduce a little bit more details for each part. Our VRC monitor is actually tracking all the VR objects in the thing, and it's using the so-called bounding boxes to present the virtual objects because they are too complicated. They can be very complicated. So finding out what their range is and what their location is, right? It could be an issue. So we're using the center, we call it the geometrical center of the object as the location. And we're using the bounding box, which is like the rectangular 3D rectangle to the box that enclosing the object as the size of the object. And we also tracks all the creation and destruction of objects, so that when an object is created, we know that it is created, so we're adding the instrumentation. And if something is destructed, we know it is destructed, then we don't need to do much actually for that. And then the VR object instrumenter is being instrumenting the newly created objects runtime. We find out based on the static analysis, we are able to tell like each object whether it is interactable by checking its listeners, right? If it's listening to a certain event, then we know it is interactable, right? And when such object is created, then we are going to instrument the code with a specific function called update trigger. And what this update trigger is doing is actually whenever the event is triggered, then we know that this object has been triggered. And then we are able to send the information to the controller, so the controller can tell that some objects are triggered, so we don't need to worry about them, and some objects are not triggered, so we are going to focus on those. So finally, everything is being everything that we just introduced is being incorporated into the exploration controller, which is actually the thing controller of the Unity. So in Unity, like for each thing, what it is doing is it has a thing initialization process, and then a thing ending after the thing is being ended, and then during the thing is running. So it's like when you're watching or when you're using the VR thing or you're in the VR thing. And then for every a frame, a physical update and a logical update is being executed. This is actually not 100% precise because actually logic update is being executed every frame, while physical update is being executed every 0.02 seconds. So Unity is handling that, but it's like the general idea is that they are going to be executed almost like every frame. And we're putting things into the physics update because we want to make sure that to avoid kind of like the influence of the frame per second, because for the logic update, it's going to be affected by the frame per second. And we're providing the 3 callback interfaces, the trigger, rotate, and move that people can implement. And also we have the tasking configurations like the moving rotation scope, moving rotation speed, and moving rotation granularity. We have the default values, but people can change them before testing, basically the developers. And we have two built-in testing strategies, the VR Monkey, which is just randomly doing the move, turn, and click. And we have the VR Grid, which is using a greedy algorithm to always move to the closest and trigger an interactable object, and then do a click. Okay, so these are the two very simple strategies. And we're going to do a live demo on that. So to make sure everything works, I'm doing a video in advance. So we can see this is a Unity framework, and we have all the scripts so that you can incorporate into the assets. And then if you want to test a thing, what you need to do is just, you can see here, you're just adding, removing everything, but adding a monkey, or in this case, we're using VR Monkey, just adding our testing script into the camera. And then you can actually run the thing. And in this time, we're using VR Monkey, so we can see that the camera is moving randomly. So which is pretty low efficiency, but you know that Monkey just works this way. It is kind of like a proof of concept for the framework, that's showing that it supports the Monkey strategy. So it's just going to be randomly moving around, just like Monkey in the Android. So let's skip this part, and we can go to the next part, which is about the VR grid part. So we can see here are the objects we're finding during the monkey testing, although we are not actually triggering them because our testing strategy is not that clever. And then we are going to see change the VR Monkey script. We're changing it to VR Grid. And now we can just run it. So we can see it is trying to find the interactive objects like the store. And the printer, and the computer, and I think there's another one. So you can see that it's greedy, so it's going to go to the closest place, but actually maybe not the most smart strategy. So it's going back to the TV. Okay. And then we go over the code a little bit. So we can see, first of all, let's see the logs. So we can see that the VR framework is able to find out like all the objects, and then it's triggering on them. It is able to find all the positions. So then we go to the code to see what is the interface. So we can see this is a VR test framework that we have the move, the turn, and the trigger. The trigger part is triggering the basic point click. So you can change the move and turn based on your new testing strategy. And this is the implementation of VR Monkey. So you can see in the move and turn, we're just using a very random technique. So basically just to move to a random location. And finally is the VR grid, where we are actually in both the move and in the turn. We need to actually track what has been triggered and what their distance from the current the camera, and then we are going to do the turn and the rotation inside. Okay, so just a brief evaluation. It's not really like we are doing it on 5 like projects with like tens to hundreds of virtual objects and tens of thousands of lines. And we can see the VR Grid is much better than VR Monkey, which is definitely kind of like as expected. And the conclusion is that it's an extensible test framework, and we have our 2 implementation online, and this link is in the paper. So that's it for the presentation, and I'm glad to take any questions. So I should leave it maybe here. that makes it.
Yeah. So, any question from the audience? Because it seems I'm the only one asking question now. But I can get started. One specific question that just occurred to me is when you show your evaluation results. In some scenario, VR Monkey just have 0% coverage.
Yeah.
Why is that?
The reason is that in the 3D, environment, it's very hard for actually VR Monkey to reach an interactable object because the search space is too large. So if you just remember our earlier monkey video, you can see that it is kept running, but it's not really triggering any interactable object. It is seeing some objects, but it's not able to interact with the object. In the GUI testing, typically the monkey is able to achieve a certain amount of coverage because you know that in the 2D interface, everywhere is buttons and where you can click. But in a 3D thing, the interactable objects are very sparse. So it's very hard for the VR Monkey to reach them.
I see. So that you mentioned that the interaction with objects, I have a follow-up question. So, because in your scene, I've noticed there are multiple objects, right?
Yeah.
It seems that different from traditional mobile testing, where it's like a single agent, you control the mobile device. Here, you actually could have multiple agents, right? For example,
That's
two
right.
different agents interact with two different objects. So did you consider extend VR test to handle multiple?
Yeah, that's a very good question. Actually, in VR test, there is both opportunities and challenges. If you have multiple cameras, maybe you can actually go in parallel, right? For example, you can have multiple cameras to reach each of these interactable objects. And in that sense, you have the opportunity to accelerate the testing. So that is one thing that when you have multiple cameras. On the other hand, there are also some challenges because sometimes you need to trigger one object before another. That is kind of similar to the GUI testing. Sometimes if you're triggering one button before another and triggering another button before this one, you're going to have different behaviors. So I think it depends on the scenario of the VR scene. That, for example, whether it allows multiple users to trigger things, or whether it has built-in kind of semantics among the VR objects interactions. So I think those are all very good potential future directions that people can implement more advanced test strategies. Many of them can be based on the VR test, and maybe some of them they need to build a little bit more, but support, for example, for multiple cameras. But I think we are definitely targeting that direction, but maybe not directly after this. But thanks for the question. That's a very good question.
I see. I do have another question because testing, we all know that we need test oracle, right? You do have this same monitor which monitor the states of the current scene. Is there any potential to develop any type of oracle to say after when the scene gets into certain states, it will be a bug or something like that?
Yeah. For the oracle part, I think it's kind of a very challenging, as we all know, that the exceptions or those kind of things that definitely can be solved by oracles. But more than that, I'm not so sure. But in VR thing, I think the complexity can be more complicated than the GUI testing. In GUI testing, there can be some rules. For example, when the controls are being placed in a certain relationship, then you kind of got an error. For example, a button is being occluded by another one. That is definitely an issue. That can be used as oracle, although I'm not so sure people are working on that. But in the VR, it's a little bit more complicated because it's more of user experience. I think that's a very open question. For the future, we are actually working on something. That is, we are using kind of like a computer vision techniques to find out whether a certain virtual object placement is reasonable or not. Yeah, but I think computer vision can play a big role there. But I think they can also be playing a big role in GUI testing. But I don't really know much. I think they definitely work there, but maybe it's not that
I actually have a work in last year FSE doing GUI testing Oracle using computer vision.
Yeah, I think that
that's
sounds
why
to me
I asked
something.
this question.
That's why I'm thinking that in GUI testing there should be people working on that, but it's just like I don't really got a one paper just in my mind. So yeah, thanks for the example. Yeah, so yeah, that's right.
Yeah.
So I think in the VR it's also the same issue, but it's more complicated because the VR is 3D perception. In many cases, the people's perception is different from 2D. So yeah.
I see. Last question is also about this monitoring. Because I know the scene you have shown, right? Those objects are all user control. Means like they wouldn't move around without user control them, right? But in reality, I have seen some VR scene that there are some objects constantly changing that are not controlled by user. If a scene has such an object, how your scene monitor gonna monitor states? Because each time you record states, the next seconds the state changes again, right? So for that kind of scenario, how your scene monitor will react?
You mean the state is changing? No, you mean the object is changing? You mean?
Yeah. For example, like when you record a state, there are some objects that are not controlled by user, right? They're just constantly changing, like some environmental object, right? For example, you have some animal running around. Let's say you have a scene in like in a jungle, right? You have animals, those kinds of things. But how you gonna like record the scene or monitor the scene if they are those constantly changing objects in your scene?
Oh yeah, I see. Thanks for the question. So for those kind of like object, I think we are kept tracking them. And if we look at this like slide, we are actually tracking them every frame. So basically we are able to tell where they are. But the issue is that whether we are able to get there, right? So for example, like there's a ball that is always moving, and then we need to have our camera to catch that. Well, that is related to, for example, how high speed you can change your camera. That is in part of the test configuration. And when the object is moving, our camera is kind of like it can be set as a kind of like chasing it. But maybe its speed is not fast enough, then possibly it's going to miss it. Currently, we don't have a very good like strategy for chasing these kind of like objects. It's more still a greedy algorithm. For example, if our speed is faster than that, and then we should be able to get that. But if we are not as fast as them, then we are not able to, for example, find a place. It's like more of like a route finding or route mapping problem in robotics. But that part we haven't explored much yet. But
I think you addressed a different question. But what I was trying to ask is that, for example, you drive a car, right? And you need to turn right at a certain point, right? But the moment you record your current location, still far away from a turning point. But the next moment, you probably need to turn. But because of the delay or something, you cannot.
I see what you mean. It's because of I see what you mean. So it's like when you are triggering something, we have like a 1 second currently, because to make sure that our performance is acceptable, we have like a 1 second delay, which means that we are performing a action every second. That basically means that after that second, the object can go away, right?
Yes. For example, you are driving a car, a moving object, something like that.
That's right. I think for the fast-moving object, that could be an issue. Although I believe that can be handled by like changing the like 1 second to a smaller. So basically, it's going to be if you go to one frame, then almost you can go anywhere. It's still like I believe it's a configuration issue. But if you're really setting your camera to move every frame, I think there could be some performance issue and also usability issue, because in that case, the recorded video may not be really usable for manual testing or manual checking if it is required. So I think that is a good question. If the object is moving really fast, I think currently we only have the solution that is to reduce that delay, so that we are able to catch it hopefully in time. But other than that, we don't really have an idea for that.
I see. All right, thanks a lot. I think we are right on time on 10:40 checkpoints. So we will go into our next presentation, which is by Mitchell. He'll be presenting syntax solidity, automated test case generation, and fuzzing for smart contracts. So Mitchell, you can share screen.
Thank you. You see the slides?
Yes, we.
Okay, great. So I'm Mitchell Olstern, and today I will present our tool called Syntax Solidity, which is a tool to automatically generate test cases and do fuzzing for smart contracts. I've worked on this tool together with Dimitri Stallenberg, Arie van Deursen, and Anibale Panicella. First, I want to give a bit of context on what smart contracts is. So smart contracts is basically a combination of a blockchain where we integrate kind of if this then that logic into it. And the term smart contract itself was coined by Nick Sawa in the early 1990s. And a more simple explanation of it would be it's an agreement between multiple parties on how a certain task needs to be executed. And the main goal of a smart contract is to reduce the trust in intermediaries. Like, for example, you can imagine you have something like eBay, you want to sell something, you want to buy something, and then you have to have an intermediary party to basically connect the two parties and also make sure that the two parties can actually trust each other. And by using a smart contract, we can actually take this party out and build in this trust into this logic that is the contract. And the second main goal of smart contracts is the automatic execution, so that when a certain party initiates a transaction and another party applies, all the different actions that need to happen based on those different initiations are automatically performed and completed when certain conditions are met. In particular, I will be focusing on Solidity. Solidity is the programming language of Ethereum, which is the most popular smart contract platform out there. And in particular, Solidity has two key properties that are important for test case generation. The first of which is it's a transactional language, which means that every time something happens in the code that's not supposed to, the language basically reverts all actions done previously within that one single transaction. And the second important property is that once a contract has been deployed to the platform, it cannot be updated anymore. And this is, of course, different than how we normally develop code, because once we find, for example, a bug or we want to add the additional features, we can actually update the application or the deployment package and redeploy this. But since this is not possible on the Ethereum platform, it's very important that we have to make sure that there's no bugs, or that at least the behavior that we're expecting is actually happening in the smart contract. On the right, you can also see a simple example of a smart contract where we basically define the contract itself. We have some events that basically indicate certain actions to the user, and we have a function that can be called by end users. So there's already some existing literature on testing for smart contracts. On one side, we have fuzzers. And a fuzzer, the difference here between fuzzing and test case generation is that with fuzzing, we only generate input data and not the complete test case itself. So there's no structure and no assertions. And although generating test input data is very efficient for finding a specific number of bugs, it doesn't allow us to actually find if the behavior of the actual behavior of the contract actually measures matches the desired behavior of the contract. And also it doesn't allow us, for example, when we capture a bug, to be able to rerun it and see if we fixed something that it would actually now basically pass the test case. On the other side, we have formal verification. This is a very old and trusted mechanism for making sure that a piece of code actually does what it's intended to do. However, formal verification is not ideal for smart contracts. First of all, because it expects a very complicated model of the expected behavior. And it's also very time-consuming to build that model. And this technique works quite well for limited scale applications that are quite small. However, if we go to bigger smart contracts and more elaborate connections between different smart contracts, it just doesn't scale as well to the proportions that we need. So to solve this, we've built Syntest. Syntest is a framework, and Syntest Solidity is one part of this, where we specifically try to generate synthetic tests for Solidity smart contracts. To do this, we make use of a genetic algorithm, and a genetic algorithm is inspired by the process of natural evolution and has 4 main steps. We have the initialization, where we generate initial random population of test cases. Then we execute these test cases and evaluate them based on a predefined fitness function, which in this case judges how well these test cases perform to our set objectives, which in this case will be branch coverage, line coverage, and those kind of testing criteria. So the way this is done, we have our framework that actually generates the test cases. We write this in the format of Truffle, which is the de facto test case of Test Suite tool for Solidity. And then we execute them on Ganache, which is a virtualization layer for the Solidity smart contract platform. Once we evaluate them, we rank them based on a selection criteria for which the test case in the population performed the best. And then based on this selection, we actually produce different variants that can then be used for the next iteration of the algorithm. So as an example, also for a test case that our framework can produce, you can see on the screen here where we basically import the contract that we want to test. Then we have a specific test case in the Truffle format where we initiate the new contract. We define a couple of input parameters. Then we call a method on the contract, and then we assert the output of the method. So we've done a preliminary study with a small selection of contracts from the overall benchmark that's been used in related work. From these different smart contracts, we can see that our tool generates already within 60% of 60-second time budget, a quite decent code coverage, in this case line coverage. And in the future, we're also planning to extend our study to include a much broader selection of smart contracts and also see if we can over time improve the performance of our tool. To increase also a bit the usability, because of course, like smart contract is a quite hyped subject, and people often don't want to set up an elaborate developer workflow to be able to write tests for their contracts and maybe do this in an iterative approach. We actually developed a web interface or web service where you can basically copy paste your smart contract, click the analyze button, and it will automatically in the backend start generating test cases for this contract, and it will give you these back as a file. Then I quickly wanted to give a demo. So also our tool is available on NPM. So in case you're interested in trying it out, you can download it from NPM, and instructions are available on NPM, GitHub, and our website. So basically, I already pasted an example smart contract in the tool. And basically, when we paste it, we click Analyze. Then in the backend, this website sends this data to the backend web service, which then generates the different test cases and then starts analyzing them and will produce some results and also give you back the test cases. since this can take quite a while depending on how long the analysis will take. First, we see the progress bar that will indicate the progress of the test case generation itself, and then it will do some processing, and eventually it will return the output. Since it's not very interesting to watch now, I will go to the CLI example, where we basically this tool can also next to the web service be used as a CLI separate tool, where we basically have a contracts folder in your working directory, and in your contracts folder, you put a contract you want to test. In this case, I picked the contract INS, and this contract has an interface at the top and the more elaborate contract at the bottom, and then I can run our tool. And also, if you run it on the CLI, it will show you a bit more sophisticated output, so it also shows you a bit more the process, the different status steps, and also the different parameters it chooses. At the top, you can see we put our search budgets. For the search algorithm itself, the algorithm we use is Dynamosa, and we have the different probabilities for the different types of mutation and crossover operators that we use in our algorithm. Then in the bottom, you can see the coverage and the progress bar. In this case, it first tries to test the token recipient interface. And of course, because we cannot really test an interface, it cannot really produce coverage for it, because of course, there's no actual callable methods. I quickly have to wait until the remaining budget is expired. Almost there. And once it tried to create coverage for the token recipient, it moves on to the next class or contract in the file, which in this case is the INS, so the main contract we want to test. And you can already see within already a couple seconds, it already produced 68% coverage. And also in the remaining time budget, it will probably go to roughly 80 or 90%, which, as you can imagine, might significantly speed up the process for the developer, given the number of branches and the size of this smart contract. So now it's already at 92% coverage, which most likely it will stay at. And at the end of the process, it will generate an report of the coverage for each different contract and what still has to be covered, so the uncovered lines in this case. I also briefly wanted to discuss the structure of the project. I think I still have some time. So our code can be found publicly on GitHub under the Syntest Framework organization, where we have the Syntest Framework itself and the Syntest Solidity project. So in the Syntest Framework, we have a generic framework for test case generation through generic algorithms. So this package contains all the different search algorithms and the different criteria and the different analysis abstracts that can then be extended for each particular tool we want to test. In the future, we also plan to extend this framework to other languages based on JavaScript, because internally, although Solidity is not written in JavaScript, all the tools that interact with it use JavaScript. And then we have the Syntest Solidity, which is the actual tool that you run to produce test cases. And on the main README, you can find instructions on how to use it. And we're also very happy to do in collaboration if someone wants to use this in their research, or if you have any questions, feel free to message us or make an issue on the repo, and we'll be happy to get you underway using our project. And if you have any questions, then I will be happy to answer those.
Right. Thank you, Mitchell, for your presentation. So I think we have one question from Elizabeth in the chat. So, actually
Okay.
two. So the first is, how are the assertion test oracle constructed? Is the code on the test assumed correct, or do the developer handwrite specification?
That's a very, indeed, since we don't have an oracle to know what the developer is actually wanting to do with their code, so we don't know the actual expected behavior, we cannot make a test case that already incorporates that. So the way we generate assertions is that we assume that what the application actually does is the expected behavior. And the one final step for the developer that remains is to double check that the assertions match the expected behavior that the developer had in mind.
Okay. The second question would be, how does your tool compare to fuzzers such as Smartian, SFuzz in terms of bug finding?
Also a very good question. So we also try to do a comparison between these different fuzzing tools and our tool. But this is quite a difficult comparison to do fairly, to do it one-on-one, because these tools work in different ways since these fuzzers only produce input data. Our tool produces complete outputs. It means that these fuzzers can actually not find full bugs. They can only find inputs for which a possible bug can happen, but you still don't know which function they might call, or maybe if you have multiple different function calls after each other, that could create compound bugs. And these fuzzing tools in general cannot find these types of bugs. I believe that most of these, like particularly I think SFuzz has some particular logic built in to find, for example, the re-entrance types of bugs and also some other types of very particular known bugs for Solidity. So for these particular types of instances, fuzzers can still, at the moment, be beneficial. We plan to incorporate these types of bug detection algorithms in our tool as well. I think our tool mainly differentiates itself by also being able to test if the desired behavior of the tool actually matches the expected behavior. That the desired behavior actually matches the behavior of the tool itself, which is something that fuzzers simply cannot do.
I think I have a follow-up question on this one. So did you try to run on certain like existing buggy or vulnerable version of the DApps or smart contract to see if your tool can detect those known bugs or vulnerability?
We are planning that. We haven't run it with actual contracts where we have known bugs in them. We have tried already to do some preliminary study by using mutation testing, where we artificially introduce bugs in the smart contracts that we have in our benchmark, and try to see how our tool performs, and seeing if the assertions that we generate can actually capture the bugs we introduced. We would generate the test cases on the version of the contract that is correct, and then we actually make changes and then see if the test would then fail the mutated contract. And from that, we can actually see that our tool is actually decently good at producing assertions that can capture bugs. I think from the top of my head, I think we had an 20% increase in mutation score by using our tool.
I see.
And we also try to do a high-level comparison with SFuzz by incorporating the algorithm that SFuzz uses in our framework itself. And there we could see that SFuzz and our algorithm actually perform better in certain use cases. So in some smart contracts, SFuzz was better, and in some smart contracts, our algorithm was better. However, since this is not a one-on-one comparison, it's really difficult to draw any conclusions from this.
All right, thank you, Mitchell. Any other questions from the audience? Because we only have 1 minute, you can unmute yourself and ask the question.
Yeah,
No,
I would have a question.
go ahead.
Since you have like a website and everything set up, do you have any plans for monetization? Like, what's your goal in general? Why are you developing this, and what are you going to do with it? It kind of looks like a startup a little.
A very good question. So at the moment, we don't have any plans to monetize our tool. In general, my research focuses on improving the process of test case generation for multiple different types of applications. And we mostly just saw a gap in the current related work for smart contract